Hello and welcome. Today, we're embarking on a journey into the fascinating world of thermodynamics. Thermodynamics is the branch of physics that deals with heat and its relation to other forms of energy and work. It's a fundamental science that explains everything from how a refrigerator works, to why a car engine runs, and even the direction of time itself. By the end of this comprehensive lesson, you will be able to, first, understand the core principles of the first and second laws of thermodynamics. Second, analyze different thermodynamic processes using PV diagrams. Third, calculate key thermodynamic quantities like work, heat, and entropy. And fourth, apply these concepts to real-world applications like heat engines and chemical reactions. Let's begin by defining some essential terms. Before we dive into the laws, we need to establish a common language. In this scene, our goal is to define the fundamental components of any thermodynamic system. First, we have the system. This is the specific part of the universe we are interested in studying. It could be a gas in a cylinder, a chemical reaction in a beaker, or even a human body. Everything outside the system is called the surroundings. The system and its surroundings together make up the universe. The boundary is the real or imaginary surface that separates the system from its surroundings. Now, systems can be classified based on what can cross this boundary. A closed system can exchange energy with its surroundings, but not matter. Think of a sealed can of soda. It can get warmer or colder, but no soda can get in or out. An open system can exchange both energy and matter. A boiling pot of water is an open system. It loses heat to the air, and water vapor escapes. Finally, an isolated system can exchange neither energy nor matter. A perfectly insulated thermos is a good approximation of an isolated system. Nothing gets in or out. Understanding these definitions is crucial for setting up and solving any thermodynamics problem. We have now defined the system, surroundings, boundary, and the three types of systems. Now that we have our terminology, let's introduce the first great principle of thermodynamics. Our objective here is to understand the first law and how it relates heat, work, and internal energy. The first law of thermodynamics is essentially a statement of the conservation of energy. It tells us that energy cannot be created or destroyed, only transferred or changed from one form to another. The mathematical expression for the first law is delta U equals Q minus W. Let's break down this equation. Delta U represents the change in the system's internal energy. This is the total energy contained within the system, including the kinetic and potential energy of its molecules. Q is the heat added to the system. If heat is added, Q is positive. If heat leaves the system, Q is negative. And W is the work done by the system. If the system does work on its surroundings, W is positive. If the surroundings do work on the system, W is negative. So, the equation says that the change in a system's internal energy is equal to the heat added to it minus the work it does. This is a fundamental accounting principle for energy. Let's work through an example to solidify this. Imagine a gas in a cylinder. The gas absorbs 100 joules of heat from its surroundings. This means Q is positive 100 joules. At the same time, the gas expands and does 20 joules of work on the piston. Since the system is doing work, W is positive 20 joules. Now, let's calculate the change in internal energy using the first law. We substitute our values. Delta U equals 100 joules minus 20 joules. This gives us a change in internal energy of 80 joules. The system's internal energy has increased by 80 joules. This example clearly shows how the first law allows us to track energy changes. We have now seen how to apply the first law to calculate the change in internal energy. In this scene, we'll focus on the W in our first law equation. Our goal is to understand how to calculate the work done by a gas and visualize it on a PV diagram. For a gas, the work done is primarily due to expansion or compression against an external pressure. Imagine a gas in a cylinder with a movable piston. If the gas expands, it pushes the piston up, doing work on the surroundings. If the surroundings push the piston down, compressing the gas, work is done on the system. The work done, W, is equal to the negative of the integral of pressure P with respect to volume 5 from an initial volume 5.1 to a final volume 5.2. The negative sign is a convention that ensures work done twice the system is positive. The integral represents the area under the curve on a PV diagram. A PV diagram plots pressure on the y-axis against volume on the x-axis. A process is represented by a path on this diagram. The work done by the gas during a process is simply the area under the curve of that process. If the volume increases, the area is positive and work is done by the system. If the volume decreases, the area is negative and work is done on the system. Let's look at a simple case. A process where the pressure is constant. This is called an isobaric process. On a PV diagram, it's a horizontal line. The work done is the area of a rectangle. The height is the constant pressure P, and the width is the change in volume, delta 5. So the work done is P times delta 5. Therefore, for an isobaric process, the work done is simply P times the change in volume. Let's do a quick calculation. A gas expands from 2 liters to 5 liters at a constant pressure of 3 atmospheres. The work done is 3 atmospheres times the change in volume, which is 3 liters. This gives us 9 liter atmospheres of work. We have now learned how to calculate work done by a gas and visualize it on a PV diagram, especially for the simple case of an isobaric process. Now, let's explore the 4 main types of thermodynamic processes. Our goal is to understand the unique characteristics of each and how they appear on a PV diagram. First, we have the isothermal process. Iso means same, and thermal refers to temperature. So an isothermal process is one that occurs at a constant temperature. For an ideal gas, if the temperature is constant, the internal energy delta U is 0. This means, from the first law, that the heat added to the system, Q, must be equal to the work done by the system, W. On a PV diagram, an isothermal process is represented by a curve called an isotherm. This curve follows Boyle's law, which states that pressure is inversely proportional to volume at constant temperature. Next is the adiabatic process. This is a process where no heat is exchanged with the surroundings. The system is perfectly insulated. Since Q is 0, the first law simplifies to delta U equals negative W. This means any work done by the system comes directly from its internal energy, causing the temperature to drop. Conversely, if work is done on the system, its internal energy and temperature increase. On a PV diagram, an adiabatic curve is steeper than an isothermal curve. This is because the temperature change during the process causes the pressure to drop more sharply during expansion or rise more sharply during compression. Third, we have the isobaric process, which we've already discussed. This is a process that occurs at a constant pressure. On a PV diagram, an isobaric process is a horizontal line. The work done is simply the area of the rectangle under this line, which is P times delta 5. Finally, we have the isochoric process. Choric refers to volume, so this is a process that occurs at a constant volume. If the volume is constant, the system cannot expand or contract, so no work is done. W is 0. The first law then tells us that delta U equals Q. Any heat added to the system goes entirely into increasing its internal energy and temperature. On a PV diagram, an isochoric process is a vertical line. Since there is no area under a vertical line, the work done is 0, which is consistent with our equation. We have now successfully identified and described the 4 main thermodynamic processes and their visual representation on a PV diagram. This understanding is key to analyzing any thermodynamic cycle. Let's put our knowledge of processes to the test with a worked example. Our goal is to calculate the work done in a multi-step process. Consider a gas that undergoes a 2-step process. First, it expands from 1 liter to 3 liters at a constant pressure of 2 atmospheres. Second, it is heated at a constant volume of 3 liters, causing its pressure to rise from 2 atmospheres to 4 atmospheres. Let's visualize this on a PV diagram. We start at point A with a volume of 1 liter and a pressure of 2 atmospheres. The first step is an isobaric expansion to point B, where the volume is 3 liters and the pressure is still 2 atmospheres. The second step is an isochoric heating to point C, where the volume is still 3 liters, but the pressure is now 4 atmospheres. The question asks for the total work done by the gas during this entire process. The total work is the sum of the work done in each step. Let's calculate the work for the first step, from A to B. This is an isobaric process, so the work done is P times delta 5. The pressure is 2 atmospheres, and the change in volume is 3 liters minus 1 liter, which is 2 liters. So the work done is 4-liter atmospheres. Now for the second step, from B to C. This is an isochoric process, meaning the volume is constant. As we learned, the work done in an isochoric process is 0. Finally, we add them together to get the total work. The total work done is 4-liter atmospheres plus 0, which equals 4-liter atmospheres. This is the area of the rectangle under the path A to B. This example demonstrates how to break down a complex process into simpler steps and calculate the total work done. We have now successfully calculated the work done in a multi-step process using our knowledge of isobaric and isochoric processes. We've covered the first law, which deals with the conservation of energy. Now, let's move on to the second law, which deals with the direction of processes. Our goal is to understand the concept of entropy and its role in the second law. The second law of thermodynamics introduces a new concept, entropy. Entropy, denoted by S, is a measure of the disorder or randomness of a system. The more ways a system's energy can be distributed, the higher its entropy. Think of a clean room. It's highly ordered with low entropy. Over time, it tends to get messy with high entropy. This is a natural tendency. The second law states that for any spontaneous process, the total entropy of the universe must increase. This is a profound statement. It means that the universe is constantly moving towards a state of greater disorder. This is why heat flows from hot to cold, and why a broken glass doesn't spontaneously reassemble itself. Mathematically, the change in entropy, delta S, is defined as the heat transferred, Q, divided by the absolute temperature, T. This equation tells us that the impact of heat transfer on entropy depends on the temperature. Transferring heat to a cold system increases its disorder more than transferring the same amount of heat to a hot system. Let's calculate an entropy change for a phase transition. Consider the melting of ice. We want to find the change in entropy when 1 mole of ice melts at its normal melting point of 0 degrees Celsius. First, we need the heat of fusion for water, which is the heat required to melt 1 mole of ice. The molar heat of fusion for water is 6.02 kilojoules per mole. This is the heat Q that is added to the system. Next, we need the temperature in Kelvin. 0 degrees Celsius is 273.15 Kelvin. Now we can calculate the entropy change. Delta S equals Q over T, which is 6,020 joules divided by 273.15 Kelvin. This gives us an entropy change of 22.0 joules per Kelvin. The entropy of the system has increased, which makes sense because liquid water is more disordered than solid ice. We have now defined entropy and used the second law to calculate the entropy change for a phase transition. This concept of increasing disorder is central to understanding why processes happen. The first and second laws are powerful, but they don't directly tell us if a process will be spontaneous. For that, we need a new thermodynamic potential. Our goal is to define Gibbs free energy and use it to predict spontaneity. This potential is called Gibbs free energy, denoted by G. Gibbs free energy combines enthalpy, entropy, and temperature into a single value that predicts the spontaneity of a process at constant temperature and pressure. The equation for Gibbs free energy is G equals H minus Ts, where H is enthalpy, T is temperature, and S is entropy. More commonly, we look at the change in Gibbs free energy delta G. The change in Gibbs free energy is delta H minus T delta S. This equation is incredibly useful because its sign tells us whether a process will occur spontaneously. If delta G is negative, the process is spontaneous. It will happen on its own. If delta G is positive, the process is non-spontaneous. It will not happen on its own, and in fact, the reverse process is spontaneous. If delta G is 0, the system is at equilibrium. There is no net change. Let's apply this to a chemical reaction. Consider a reaction with a change in enthalpy of negative 100 kilojoules and a change in entropy of negative 200 joules per Kelvin. We want to find the temperature at which this reaction becomes spontaneous. For the reaction to be spontaneous, delta G must be less than 0. So we set our equation to be less than 0. First, we need to make sure our units are consistent. Let's convert delta H to joules. Now we have negative 100,000 joules minus T times negative 200 joules per Kelvin is less than 0. Rearranging the inequality, we find that T must be less than 500 Kelvin, so the reaction is spontaneous at any temperature below 500 Kelvin. This example shows how Gibbs free energy provides a clear criterion for spontaneity. We have now defined Gibbs free energy and used it to predict the spontaneity of a process based on temperature. Now, let's explore a powerful application of thermodynamics: heat engines. Our goal is to understand how heat engines work and how their efficiency is limited by the second law. A heat engine is a device that converts heat energy into mechanical work. Think of a steam engine or a car engine. They take heat from a hot source, do some work, and then dump the remaining heat into a cold sink. We can represent this with a simple diagram. Heat, Q_H, flows from a high-temperature reservoir, T_H. The engine does work, W, and rejects heat, Q_C, to a low-temperature reservoir, T_C. The first law tells us that the work done is the difference between the heat absorbed and the heat rejected. So W equals Q_H minus Q_C. The efficiency of an engine is defined as the ratio of the work output to the heat input. Efficiency, ETA, is W divided by Q_H. Substituting our expression for W, we get that efficiency is 1 minus Q_C over Q_H. The second law of thermodynamics places a fundamental limit on this efficiency. It states that no engine can be more efficient than a reversible engine operating between the same two temperatures. This theoretical maximum efficiency is called the Carnot efficiency, is given by 1 minus the ratio of the cold temperature to the hot temperature, both in Kelvin. This means that to build a more efficient engine, you need a hotter hot reservoir, or a colder cold reservoir. You can never achieve 100% efficiency, because that would require a cold reservoir at absolute zero, which is impossible. Let's calculate the maximum possible efficiency for a real-world engine. A car engine operates with a combustion temperature of 2000 Kelvin and exhausts gases at 1000 Kelvin. What is its maximum theoretical efficiency? Using the Carnot efficiency formula, we have 1 minus 1000 Kelvin divided by 2000 Kelvin. This gives us an efficiency of 0.5 or 50%. This is the absolute best this engine could ever perform. In reality, friction and other irreversibilities would make its actual efficiency much lower. We have now explained how heat engines work and calculated their maximum theoretical efficiency using the Carnot cycle, a direct consequence of the second law. Just as heat engines convert heat into work, refrigerators and heat pumps do the opposite. Our goal is to understand how these devices work and how their performance is measured. A refrigerator is a device that uses work to transfer heat from a cold reservoir to a hot reservoir. It's a heat engine running in reverse. You do work on the system to move heat against its natural flow from a colder place to a warmer place. The diagram is similar to a heat engine, but the arrows are reversed. Work, W, is put into the system to move heat, Q_C, from the cold reservoir, T_C, to the hot reservoir, T_H. The performance of a refrigerator is measured by its coefficient of performance, or COP. The COP is the ratio of the heat removed from the cold reservoir to the work input. A higher COP means the refrigerator is more efficient. Using the first law, W equals Q_H minus Q_C, we can rewrite the COP as Q_C divided by the difference between Q_H and Q_C. Like heat engines, refrigerators also have a maximum theoretical performance, given by the Carnot COP. The Carnot COP is the cold temperature divided by the difference between the hot and cold temperatures. Again, all temperatures must be in Kelvin. A heat pump is essentially the same device as a refrigerator, but its purpose is different. Instead of cooling a space, it's designed to heat a space. A heat pump takes heat from a cold source, like the outside air, and uses work to pump it into a warm space, like your house. Its performance is also measured by a COP, but the definition is slightly different. For a heat pump, the COP is the heat delivered to the hot reservoir, Q_H, divided by the work input, W. The Carnot COP for a heat pump is the hot temperature divided by the difference between the hot and cold temperatures. Let's calculate the COP for a refrigerator. A refrigerator operates between a cold reservoir at 270 Kelvin and a hot reservoir at 300 Kelvin. What is its maximum COP? Using the Carnot COP formula, we get 270 divided by 300 minus 270, which is 270 divided by 30, giving a COP of 9. This means for every 1 joule of work input, the refrigerator can remove 9 joules of heat from the cold space. We have now explained the operation of refrigerators and heat pumps and calculated their maximum performance using the Carnot COP. So far, we've mostly considered ideal gases. But what about real gases? Our goal in this scene is to understand how real gases differ from ideal gases, and how to describe them using the van der Waals equation. The ideal gas law, PV equals nRT, is a great approximation, but it's based on 2 key assumptions that aren't perfectly true for real gases. First, it assumes that gas molecules have no volume. Second, it assumes there are no attractive forces between the molecules. At high pressures and low temperatures, these assumptions break down. The molecules get closer together, their volume becomes significant, and the attractive forces start to matter. To account for these real-world effects, we use the van der Waals equation. The equation is P plus A times N squared over V squared, all multiplied by V minus NB, equals nRT. Let's look at the 2 correction terms. The A term corrects for the attractive forces between molecules. These forces pull the molecules inward, reducing the pressure they exert on the container walls. So we add this term to the measured pressure to get the ideal pressure. The B term corrects for the finite volume of the molecules themselves. The molecules take up space, so the actual volume available for them to move in is less than the container volume. We subtract this term from the container volume. The constants, A and B, are specific to each gas and are determined experimentally. Let's do an example. We'll calculate the pressure of a real gas. What is the pressure exerted by 1 mole of carbon dioxide in a 22.4 liter container at 273 Kelvin, using the van der Waals equation? First, let's find the pressure using the ideal gas law for comparison. P equals nRT over V. Plugging in the values, we get a pressure of 1 atmosphere. This is the ideal pressure. Now, let's use the van der Waals equation. We need the constants A and B for carbon dioxide. For carbon dioxide, A is 3.59 liters squared atmospheres per mole squared, and B is 0.0427 liters per mole. Rearranging the van der Waals equation to solve for P, we get P equals nRT over V minus NB minus A times N over V squared. Plugging in all the values, we calculate the pressure. The first term, the ideal pressure, is 1 atmosphere. The second term, the correction for attractive forces, is about 0.007 atmospheres. The third term, the correction for molecular volume, is about 0.008 atmospheres. The final pressure is 0.999 atmospheres. It's very close to the ideal pressure because the conditions are not extreme, but it is slightly lower due to the attractive forces. We have now explained the limitations of the ideal gas law and used the van der Waals equation to calculate the pressure of a real gas, accounting for molecular volume and attractive forces. Let's shift our focus to chemical reactions. Our goal is to understand how thermodynamics can predict the direction of a reaction and how to manipulate it. We've already seen that a reaction is spontaneous if its Gibbs free energy change, delta G, is negative. But what happens when delta G is 0? This is the point of chemical equilibrium. At equilibrium, the rates of the forward and reverse reactions are equal, and there is no net change in the concentrations of reactants and products. The position of equilibrium is described by the equilibrium constant, K. The equilibrium constant, K, is related to the standard Gibbs free energy change, delta G naught, by the equation delta G naught equals negative RT natural log of K. This equation is incredibly powerful. If you know the standard Gibbs free energy change for a reaction, you can calculate its equilibrium constant, and vice versa. Now what if a system is at equilibrium and we disturb it? This is where Le Chatelier's principle comes in. Le Chatelier's principle states that if a system at equilibrium is subjected to a change, it will adjust itself to counteract the change and restore a new equilibrium. Let's consider a classic example, the Haber-Bosch process for synthesizing ammonia. The reaction is nitrogen gas plus 3 hydrogen gas molecules in equilibrium with 2 ammonia gas molecules. The reaction is exothermic, meaning it releases heat. Let's see how we can shift the equilibrium to produce more ammonia. First, we can increase the pressure. The system will try to relieve the pressure by shifting to the side with fewer gas molecules. The product side has 2 molecules, while the reactant side has 4. So increasing pressure shifts the equilibrium to the right, producing more ammonia. Second, we can decrease the temperature. The system will try to counteract this by producing heat. Since the forward reaction is exothermic, decreasing the temperature shifts the equilibrium to the right, again producing more ammonia. This principle is a cornerstone of chemical engineering, allowing us to optimize reaction conditions to maximize product yield. We have now connected Gibbs free energy to the equilibrium constant and used Le Chatelier's principle to predict how a system at equilibrium responds to disturbances. Finally, let's explore how pressure and temperature affect the physical state of a substance. Our goal is to understand phase diagrams and the special points on them. A phase diagram is a graphical representation of the physical states of a substance under different conditions of temperature and pressure. It's a map that tells you whether a substance will be a solid, liquid, or gas at any given temperature and pressure. Let's look at a typical phase diagram. The axes are pressure and temperature. The diagram is divided into 3 regions: solid, liquid, and gas. The lines on the diagram represent the conditions where 2 phases are in equilibrium. The line between the solid and liquid regions is the melting or freezing curve. The line between the liquid and gas regions is the vaporization or condensation curve. And the line between the solid and gas regions is the sublimation or deposition curve. There are 2 very important points on a phase diagram. First is the triple point. This is the unique combination of temperature and pressure where all 3 phases, solid, liquid, and gas, can coexist in equilibrium. Second is the critical point. This is the temperature and pressure above which a substance can no longer exist as a distinct liquid and gas. The 2 phases merge into a single homogeneous fluid called a supercritical fluid. Supercritical fluids have fascinating properties. They can diffuse through solids like a gas, but they can dissolve materials like a liquid. This makes them useful for applications like decaffeinating coffee. Let's look at the phase diagram for water, which has a unique feature. Notice that the solid-liquid line for water slopes to the left. This is unusual. For most substances, it slopes to the right. This negative slope means that increasing the pressure on ice at a constant temperature can cause it to melt. This is why ice skates glide so easily. The pressure from the blade melts a thin layer of water, reducing friction. We have now learned how to interpret phase diagrams, identify the triple and critical points, and understand the unique behavior of water's phase diagram. We've covered a vast amount of material today. Let's take a moment to recap the key concepts we've explored. We started with the first law of thermodynamics, the law of energy conservation, which relates heat, work, and internal energy. We then introduced the second law and the concept of entropy, a measure of disorder, which dictates the direction of spontaneous processes. We saw how Gibbs free energy combines these ideas to provide a clear criterion for spontaneity at constant temperature and pressure. We analyzed the 4 main thermodynamic processes: isothermal, adiabatic, isobaric, and isochoric, and visualized them on PV diagrams. We applied these principles to real-world systems like heat engines and refrigerators, understanding their efficiencies and coefficients of performance. We also ventured beyond ideal gases to describe real gas behavior with the van der Waals equation. And finally, we explored chemical equilibrium and phase diagrams, seeing how thermodynamics governs the states of matter and the outcomes of chemical reactions. Thermodynamics is a powerful and elegant framework for understanding the universe around us. I hope this comprehensive lesson has provided you with a solid foundation in its core principles and applications. Thank you for watching.